Hello students. So in this in the previous video we have discussed about structural and geometrical isomerism. Okay, so we'll just continue with the remaining part. So we'll start with optical isomerism. So optical isomerism is is a property, say optical activity. Okay, first you have to know what is optical activity. Okay, means or which compounds are optically active, which are optically inactive. Okay, so I have discussed about this optical activity in my inorganic chemistry video, say coordination compounds. So you just check it once there, you will understand it. Say if you have a solution, okay, and if you pass plain polarized light through this solution, and if it rotates the plane of that polarized light, then we can say that the compound that is present in the solution is optically active. Okay, now if it rotates the light in clockwise direction, so it is called D isomer, and if it rotates the light in anti-clockwise direction, it is called a L isomers. Okay, so both the pairs are present 50-50%. Okay, then it is called a racemic mixture. Okay, so this D and L isomers, they are nothing but your mirror images. Okay, and as a whole they are called enantiomers. Okay, now see, mirror image means what? Say you have this letter A. Okay, if you draw a mirror image, okay, so mirror image of A will be this one only. Okay, and if you have a letter B, then for B the mirror image will be this one. Okay, now see what are enantiomers. Actually, this mirror image na of A, if we place this image of A exactly on top of A, it will just be like this. Okay, means it will be same, so it will be superimposable. Means if we place one A on top of another A, it is exactly same. Okay, but in case of B, if you place this isomer image on top of this original B, so you'll get somewhat this type of arrangement. Okay, so this is called your non-superimposable mirror image. Means the mirror image and the original object, they are non-superimposable. Okay, so this type of pairs na, where the mirror image and the original object are non-superimposable, these are called your enantiomers. Okay, and where they are superimposable, they are not enantiomers. Okay, so these enantiomers, these are represented by two forms. Okay, so two types of representation are there, so two formulas are there. First one is your wedge and dash formula or form, and second one is your Fisher projection formula. Okay, so wedge and dash means what we will do. Say we have a tetrahedral structure, say we have a carbon attached to four different halogens. Okay, now this one, you see, it is the structure is somewhat like this. Say two atoms, this fluorine atom and this iodine atom and the carbon. Okay, these three atoms, they are present in the plane of the paper. Okay, and you have a bromine that is above the plane of the paper, and you have a chlorine that is below the plane of the paper. Okay, so this is tetrahedral geometry basically. Okay, now see this above the plane of the paper. Say if you are a viewer, okay, and you are observing to this diagram, say this paper from top side. Okay, so you are observing from this way. Okay, from this direction you are viewing it. So this bromine, it is towards you. Okay, if the bromine is towards you, it is represented by this solid line is called a wedge. This thing is called a wedge. Okay, and the chlorine, it is away from you. Okay, it is far away from you and is behind the plane of the paper, so that is not visible to you. Okay, so that's why it is represented by a dash. Okay, so this formula, the bonds that are towards you, the bonds that is away from you, are represented by wedge and dash. So that's why this formula is called your wedge and dash formula. Okay, and the simple lines means that it is present in the plane of the paper. Okay, and wedge means it is towards you, and dash means it is away from you. Okay, so this type of notation or formula is called your wedge and dash formula. Now one more thing I forgot to tell you, that for optical activity na, in organic compounds, the most important thing is that you should have a chiral carbon. Okay, and it is represented by a star symbol. Okay, now carbon represented by a star symbol is called your chiral carbon. And how you will identify that whether a carbon is a chiral carbon or not, you just have to check for all the different atoms that are attached to carbon. Okay, now if all the atoms that are attached to carbon are different, okay, so you have A, B, C and D, okay, all the atoms are different, then the carbon is called your chiral carbon, and then the compound is called optically active compound. Okay, in this case you have four different halogens, so that is the chiral carbon. Okay, so this thing is very important. Second thing is that same this Wejen dash formula na, like this you can also draw, means also have a different representation formula. It's called your Fisher projection formula. Okay, so Fisher projection formula, it is just nothing but you just draw two lines. Okay, so one is horizontal, one is vertical. So you just draw two lines, one is horizontal, one is vertical. Okay, so horizontal line, it means the atoms that are away from you or towards you. Okay, means the atoms that are not present in the plane of the paper. And the vertical lines, it tells you about the atoms that are present in the plane of the paper. So you just see this structure, you just consider, say this is fluorine. Say just let us erase this one. Okay, simple thing. So say this is carbon. Okay, this fluorine, it is in the plane, and this iodine also we can draw in the plane. Okay, and this bromine that is away from you, means above the plane na? Means sorry, that is towards you, means above the plane, we'll draw it this side, and the dash we'll draw it this side. Okay, so it is like this. You will get fluorine here, iodine here, chlorine here and bromine here. Okay, so this notation na, is called a Fisher form, this one. Okay, so this is the Fisher form, Fisher projection formula. It is this structure. Okay, and for this structure, you see the horizontal line are the bonds that are above the plane or below the plane. Okay, and the vertical line tells us about the bond that is in the plane of the paper. Okay, so this representation is called your Fisher projection formula. Now for this one, the mirror image is this one, and you see this one, if you place this image na on top of this one, it is non-superimposable. Okay, so these are enantiomers. One will be D, one will be L. Okay, so this is the basic definition of enantiomers. Okay, and representation can be done in two ways. One is Wedge and Dash formula, another one is your Fisher projection formula. Okay, now let us move on to the next part. Next is your RS configuration. Okay, so RS configuration is very important, because you see this enantiomers na, enantiomers for you just have, we just did cis trans, EZ, syn NT. Okay, but for enantiomers, say if you draw Fisher projection formula, okay, or Wedge and Dash formula, then we cannot assign EZ nomenclature, because EZ, cis trans, those are for double bonded carbons. Okay, means geometrical isomers where you have double bonded carbons, you can use those EZ, cis trans and syn and anti. Okay, but here in same carbon you have four different atoms. Okay, then how we will assign? So for this type of systems now, we have a separate configuration or separate nomenclature. It's called RS nomenclature. Okay, so RS is simply, you just see that if same thing, just like EZ now, we'll assign priority to the four atoms. In EZ, what you have to do, we used to assign priority to two atoms. In RS, what we will do, we'll assign priority to all the four connected atoms to the carbon. Okay, and we'll follow the same rules. We'll check for atomic number. If atomic number is same, we'll check for atomic mass. If atomic mass is also same, we'll check for the next connecting atom. Okay, the same rules you have to follow. So if the minimum priority, say out of these four groups na, say we have A, B, C, D, so we have 1, 2, 3, 4. Okay, so these are the priority of the groups. Okay, if the minimum priority group, say the fourth group, is in the horizontal line, okay, then R means anti-clockwise, and S means clockwise. Means if the rotation is clockwise, we will write S. If the rotation is anti-clockwise, we will write R. Okay. And if the fourth group, say the least priority group, is in the vertical line, okay, then it will be just opposite. Means clockwise rotation will give us R, and anti-clockwise rotation will give us S. Okay, so you just remember these 2 points. These are very very important. Okay, if you remember this and you know the rules for finding out assigning priority, then you can easily write RS configuration for any compounds. Okay, so just let us go for the examples. You see this first example now. This is the chiral carbon because it is attached to 4 different atoms or groups. Okay, so you see priority how will give. You have a chlorine has higher atomic number, so it will be 1. Then oxygen is second highest, so it is 2. And then carbon, so it is 3. Okay, so our movement now of arrows will always be 1 2 3. Okay, you will just neglect the 4th atom, so movement of arrow will be 1 2 and 3, from 1 to 2, 2 to 3. Okay, the 4th atom will always be neglected. So in this one, you see, if I'm moving from 1 to 2, 2 to 3, we are going in in clockwise direction. We are moving in this direction. Okay, like this. So you see the least priority group is in horizontal, means we have to follow this rule. Least priority group horizontal, this rule. So clockwise will give you S. Okay, so that's why it is S. Okay, same thing this one. You see least priority group hydrogen is in vertical line, and we are going in anti-clockwise direction. Okay, anti-clockwise vertical, anti-clockwise vertical will give you S. So this one is also S. This is anti-clockwise. Okay, then third one, you see this one is also S. Oxygen is first priority, then nitrogen, and then carbon. Okay, hydrogen is least priority, so we are going anti-clockwise. Least priority is in vertical position, so it is S. Okay, then if you have this type of things where you have more than one chiral carbons, okay, so more than one chiral carbons, you have to assign RS nomenclature to all the carbons, means all the chiral carbons. Okay, so now see, let us consider this carbon, the upper one. Okay, so upper one is connected to oxygen, carbon and hydrogen. So oxygen is 1, first priority. Now see, this one is also carbon, and this is also a carbon that is attached to this one. Okay, so you just check for the next atoms. In this one it is hydrogen plus hydrogen plus hydrogen. Okay, and in this one, for this carbon, it is oxygen plus carbon plus hydrogen. So this is highest, so this is 2, this is 3, this is 4, and we are going clockwise. Least priority in horizontal position, clockwise least priority horizontal position is S. So this carbon, the upper carbon, is S. Okay, and if you check for the second carbon, it is giving anti-clockwise in horizontal, so it is R. So it is 2R 3S. Why 2 3? You just check for the longest chain. Longest chain is 1 2 3 4, means top, bottom to top. Okay, so it is 2 position you have R configuration, and 3 position you have S configuration, so it is 2R 3S. Okay, so in this way you can find out RS nomenclature for all the chiral centers. Okay, you just solve some examples, and just if you have any doubts, you just show me. Okay, so let us move on to the next part. Next part is that how to find out that number of optical isomers. Okay, so same thing, if you have symmetrical molecules, then you will use this formula. Number of DL will be given by this formula, number of meso will be given by this formula, and total number of isomers is the sum of DL and meso. Okay, and if you have unsymmetrical alkenes, you will use this upper formula. Okay, these 3 formulas, and N is just the number of chiral carbons, so you just use this formula, you'll get your answer. So you can use this one for finding out the total number of optical isomers. Okay, so one more thing, what is meso compound? Okay, so meso compound means, say you have this type of compounds now, say COOH, and you have COOH. Okay, like this. So this you have OH, here you have H. Okay, so this type of compounds where you can draw a plane of symmetry like this. you can cut the compound into two equal halves na. So this type of compounds are called your meso compounds. Okay, means in wherever you can draw a plane of symmetry, means you can cut a compound into two equal halves, so it is called your meso compound. Okay, next let us move on to stereoisomerism. Okay, this is the last topic for isomerism. So stereoisomerism means there will be difference in stereochemistry, means number of atoms will be same for uh, different compounds, but just there will be difference in the stereochemistry. Okay, so the stereoisomerism, we have conformational isomers. Okay, so there are two types of conformations that are possible. One is your Newman projection, another one is Sawhorse projection. Means for representation of stereoisomers, two projection formulas are used. One is Newman, one is Sawhorse. Okay, so first we will discuss Sawhorse. Sawhorse means say you have a carbon, say ethene molecules. Okay, say you have CH3, okay. So this molecule you will view it from a sidewise, means a side angle. Okay, so if you view this one from the side, we'll just have these two views. Okay, it just looks like a horse with two front legs upside. Okay, just like a unicorn, how it stands in two legs, so just like that. So this ethane molecule will be visible like this. Okay, so this type of representation of the ethane molecule is called a sawhorse representation. Okay, and this one is not that important, the Newman one is important, so we'll discuss the Newman more detailed way. So sawhorse, you just see it can be of two types, one is staggered, one is eclipsed. Okay, now see staggered and eclipsed. In ethane you have two carbons, the first carbon is this one, second one is upper one. Okay, now both the carbons have three hydrogens. Okay, now if you look from this side, okay, from this front side, and if one hydrogen overlaps with the backward hydrogen, say front hydrogen overlaps with the back hydrogen, then the structure is called your eclipse structure. Okay, and if you look from front side, if all the hydrogens, say 6 hydrogens are visible, then it is called a staggered structure. Okay, and in this structure you see the angle between hydrogen carbon hydrogen is called a dihedral angle, means this angle. Okay, dihedral angle. So for staggered, the dihedral angle is 180 degree, and for eclipsed the dihedral angle is 120 degree. Okay, because eclipsed is will be visible like this only now. So if you just look from this side, it is like this. Okay, so 120 degree. Okay, so in the second formula we have the Newman projection. So Newman projection formula is very important for your exam point of view. So in this projection formula, what we do, we just represent the front carbon with a dot and the backside carbon with a circle. Okay, so it is also of two types, say eclipsed and staggered. Eclipse means if the front carbon having atoms, say if the front carbon has three hydrogens now, if it overlaps with the back carbon, then it is eclipsed, and if it does not overlaps with the back carbon, then it is called staggered. Okay, and always remember that the staggered form is more stable compared to the eclipsed form. Why it is more stable? Because these hydrogens are far apart, so steric repulsion is very less. Okay, so let us see some examples. Say we have to draw the conformations of ethane. Okay, so ethane, we'll start it from eclipse form. Okay, so and we'll just rotate this one by 60 degree. We're just rotating the backside carbon by 60 degree. Okay, you have to keep in mind that the first carbon will be fixed. Okay, that the front carbon will be fixed, only the back carbon you are rotating by 60 degree in all the steps. Okay, so we'll start it from eclipse, say 0 degree. Then if you move 60 degree, this HA backside hydrogen will come in this position, this is called staggered. Then again if you move 60 degree, this will come in this position. You just see that front hydrogens are fixed. Okay, means front carbon is fixed, the backside hydrogens are labeled as A, B and C, and we're just rotating it by 60 degree. Okay, so after rotation, you see after 6 structures we'll get the first structure back. Okay, means 0 degree and 360 degree, they are same. Okay, now see, in this course of rotation now we are getting 6 different types of arrangements. Okay, 6 different types of arrangements. 3 arrangements are your eclipsed, say first structure, first one, third one and fifth one, these 3 are eclipsed, and the second, fourth and sixth are staggered. Okay, so order of stability, staggered is more stable than eclipsed. Okay, next if you do it for butane na, what we will do, we'll get this type of arrangement. Say you will get CH3 eclipsed, means this is the most unstable structure, because you see CH3 groups are bulky groups. Okay, and bulky groups same side, they are having very high steric repulsion. Okay, so that's why this is the most unstable structure, the first one. Okay, second one is staggered structure, and second, fourth and sixth are staggered structures. This one, second, fourth and sixth are staggered structures. Okay, now see, out of the staggered structures now, the fourth structure, that is 180-degree, is called your NT because you see the CH3 groups are 180-degree apart. Okay, and this is the most stable structure because the bulky groups are far apart. Okay, but other two staggered structures now, where the bulky groups are 60-degree apart. Okay, so these two structures are called your gauge structures. Okay, and order of stability for gauge structure is less than NT because you see they are nearer, so there will be some steric repulsion. Okay, and out of the eclipse structures, you see first structure is your fully eclipsed because the CH3 and CH3 are overlapping each other. Okay, and the third and the fifth structure, the CH3 is being overlapping with the hydrogen. Okay, so that is called partially eclipsed structures. Okay, so the order of stability will be like this: NT will be the most stable, then gauge, then partially eclipsed, and then fully eclipsed. Okay, so this is what we have from conformation, say stereoisomerism. Okay, this conformations of ethane and butane are very important. This order of stability, this question came in previous year also, and I guess this year also this question will be coming because in 2019 say this question didn't came, say, so this year I guess this questions will be coming. Okay, now see, one more question is there, you just check this one. Say for, you have this one, say you have CH2, you have OH and you have OH. Okay, so for this one you have to draw the conformations. Okay, means ethane 1,2 diol. Okay, so for this one, what you will get, you will get same forms na, in place of CH3 you will write OH. Okay, so one OH will be here and another OH will be here. Okay, this is one gauge form, and NT form will be like this. One OH will be here, one OH will be here, and this will be H, and H. Okay, now what is the thing that I want to tell you is that in the previous example for this one na, butane, you got that NT. In the previous example for butane, NT was more stable. Okay, NT was more stable than gauge. Okay, but in this case gauge will be more stable than NT. Why? Because you see this gauge structure na, this hydrogen, it is attached to oxygen. Oxygen is more electronegative. Okay, so hydrogen is having a delta plus charge, oxygen is having a delta minus charge. Okay, hydrogen is having plus charge, oxygen is having a delta minus, and this oxygen is also electronegative. So there is a possibility to form hydrogen bond between this oxygen and this hydrogen. Okay, so this formation of hydrogen bond will give you extra stability to this gauge structure. Okay, So for this type of things na, where you will have hydrogen bonding possible, so what you will do, you just check for this hydrogen bonding. Okay, if hydrogen bonding is present, then gauge will be more stable than NT, and if hydrogen bonding is not possible, then NT is more stable than gauge. Okay, so with this your isomerism is over. So you just read the concepts and try to solve questions. Okay, just for every chapter what you do, you just try to finish the concepts in 1 hour, and then 2-3 hours say you just keep solving questions. Okay, for any subject whatever you study, so that will be helping you, because if you know the concepts, okay, but if you don't solve questions now, you won't be able to answer. Because see, it is not that how much you know, it should be like that how much you can apply, because without applications it is of no use to keep with your knowledge. Okay, so you just solve as many questions as you can. Okay, so if you have any doubts, you just ask me anytime. Okay, just text me in my number or anything. Okay, just post the question anywhere, so I'll just solve it and I'll just explain it to you. So thank you.